So welcome to the Royal Society. My name's Marcus Du Sautoy. I'm the Professor for the Public Understanding of Science in Oxford and also a Professor of Mathematics. Actually, both subjects which I think are very relevant to tonight's debate. U and AI. Certainly mathematics underpins a lot of the AI that we're going to be talking about, applied to many different bits of society, and it's going to impact society massively over the coming years, which is why a public debate is so important. Actually, I made a program about AI some years ago for the Turing anniversary in 2012 with the BBC. And I must say, at the end of that program, we were all a bit disappointed about the state of AI. It all seemed to not sort of be coming to any kind of exciting fruition. But that has so changed over the last few years. I was very lucky to be invited onto a committee we had here looking at the impact that AI and machine learning is having on society, which culminated in a report that we wrote, which is sort of forward-scoping, trying to understand the impact of this exciting time. We've talked a lot about AI winters. This seems to be like an AI heat wave that we're experiencing. That report was very well received, and we wanted to continue the debate. So tonight's event is part of a continuing dialogue that we're hoping to have with you and scientists who are using their machine learning and AI in their practice. It's a series of events which are supported by DeepMind. We were very lucky to have Demis Hassabis on Monday, kicking the series off. This is the second of a whole series of events which will be happening here in London and also outside of London as well, in Manchester. So I'm very excited to have four amazing speakers with such a range of different applications and stories to tell. So I think it's we'll crack on to hear some of these stories. And the first story is going to come from Steve Young. He holds a joint appointment at Cambridge University, where he's Professor of Information Engineering, and also at Apple Computer, where he's a member of the Siri development team. Now, it's interesting, I asked Siri to give me a little bit of information about Steve. Turns out Steve is also a quarterback for an American football team, but I think it might be another Steve Young, that one. But anyway, Steve will talk to us about the rise of the virtual personal assistant, how we currently interact with our computer-generated aids, and the potential for the future. Please welcome Steve Young.
Well, thank you, Marcus. That's not the first time that's been mentioned. I had to ask the first time I had to ask what a quarterback was, but that was a long time ago. As Marcus said, I'm a professor at Cambridge University, and I also work for Apple. And I must stress, tonight I'm speaking with my university hat on. Nothing I say should be taken as being anything to do with Apple's strategy for developing Siri. So let me start with a definition. Virtual personal assistant, an intelligent conversational agent that can communicate in natural language with access to your personal data and with the authority to execute transactions on your behalf. That's my definition. Now, we're not there today, so think of a smarter version of Alexa or Siri that's personalized to each individual. It actually works for you rather than being a shared service run by whether it's Apple or Amazon. Now, I'm going to call them VPAs. VPAs will not just talk to their owner, they'll also talk to each other. This is just a short step away. Here's an example. Bob asks his assistant, he says, I need to meet with Tim urgently. Bob's assistant communicates with Tim's assistant, and Tim's assistant says, Tim's free at 4 p.m. So Bob says, okay, great. But then Bob's assistant looks into Bob's diary and says, shall I rearrange your 4:30 p.m. with Sue? Because he's probably not going to make it. Bob says, yes, do that. And Bob's assistant then rearranges Sue's meeting with effectively delegated authority. Bob has gone off to do something else. Now, this is the sort of thing that will be happening in the not too distant future. Now, I'd like to explain a little bit about how these virtual personal assistants work. And I've got a block diagram here. I can only give you a very quick skim over it. But essentially, it's a pipeline of processing components. The first one, ASR, that's automatic speech recognition. This converts what the user says into into a sequence of words, and then a component called natural language understanding extracts the meaning from that sequence of words. And something called a belief tracker integrates what the user's just said with what might have been said previously in the conversation. And all of this is assembled in some kind of internal data structure, which we call the belief state. And then the dialogue manager has to decide what to do next. Shall it ask the user for more information or confirmation to do something, or shall it just go ahead and do the action? Let's just give me a quick example. So the user says, find an Indian restaurant nearby, and you can see that above the belief state, it's filled in some information in some abstract form. We're looking for a restaurant, locations nearby, but it's not sure what kind of food the user asked for. So the dialogue manager thinks, I need to clarify that. So it asks the user, was that Indian or Italian? The user responds, Indian, but not too expensive. And the dialogue manager updates its the belief tracker updates the belief state. The dialogue manager now sees it has a complete query. It looks in the world knowledge base, the World Wide Web. It looks in its personal data, and it comes back and says, Vedanta is just around the corner, and you've been there before. So this is something Siri today might tell you Vedanta's just around the corner, but it won't tell you that you've been there before because it's not personalized to you. Now, these systems are complicated. Each of those boxes in that previous diagram will have consumed many academics, many years of research trying to figure out how to do those particular functions. And until fairly recently, a lot of it was handcrafted in rules, bits of machine learning, but not a lot. But as Marcus said, that's all changed in recent years. And it's not just that AI, machine learning, and especially deep learning, it's not just that deep learning can do things with more accuracy. It's also, it really is a plug-and-play technology. And what we've got today is loads of building blocks which do things for us, and we can just pull them off the shelf. So there's something called word embedding, which maps word symbols into a continuous space. That's very useful for realizing that two words mean very similar things. They get projected to the same point in this space. We don't need to worry about that anymore. It also works very well for using multilingual understanding because words from different languages can be made to project into the same space. Convolutional networks can automatically find features in the raw data and save us from having to handcraft our classifiers. And then more recently, sequence-to-sequence models have been developed, which are very good at you can train them, say, here's a bunch of input sequences, a bunch of output sequences, and the model learns to map one into the other. The classic example is in machine translation. When you use Google Translate, you say something in English, translate into German. It's a sequence-to-sequence model that's doing that. But you can use them all over the place in any kind of natural language processing system. And all this is supported by high-quality software tools. So what this has allowed us to do is to scale up. And we need to. These systems have to support millions of users. For example, Siri handles just over 1 billion transactions a week. So there's huge amounts of data, and we have to be able to develop the system. The only way moving forward is to use this data-driven learning. So that's the real impact of deep learning. Just to give you a quantitative view of this, speech recognition is a classic example. This plot shows the word error rate, so small is good, against time, on a particular test set that's been around a long time. It's called the switchboard corpus. It's conversational speech. It's actually family and friends talking to each other. They were paid to do it a long time ago, so it's from the 1990s. When I first started working on this, the error rate was over 50%. We worked on it quite hard through to the mid-2000s, and the error rate sort of plateaued about 20% using the technology of the time. Deep learning came in and the use of deep neural networks, and that has had a dramatic effect on performance. And the most recent results published on this data set have an error rate of less than 6%, which if you ever listen to this data is absolutely remarkable because I can't understand what's being said half the time. So the technology is in place. We're not there to fully personalize virtual assistants just yet, but we're getting close. There are technical challenges. We need to reduce our dependence on so-called supervised learning, because right now what we do is we collect data and have to label it. We need to get away from that. Our personal agent needs to have more conversational skills. It needs to be able to handle things like interruption and the way humans maneuver to take the floor. And it also needs to incorporate common sense reasoning and inference, and that's probably one of the hardest things that's yet to be achieved. But there are other challenges as well. Societal challenges, ensuring that VPAs are a force for good. Should they have some ethics? Developing policy to manage privacy and trust. Establishing a legal framework for liability. Now, I'm not sure how serious a problem that is, but it's possible. Let me just say a little bit more about each of those. So ethics. Now, this is a bit in your face, so I apologize, but what happens if you say to your personal assistant, tell me about creationism? Should the assistant say, well, I'll tell you what it is, but there's no scientific basis for it? Or more in your face, should it tell you how to make a nail bomb? Or should it show you what you asked for? Should it refuse to show you? Should it indeed report you to the authorities? Okay, it's a bit of a cartoon example, but you can see that there is an issue here, potentially. So should there be a code of ethics for virtual assistants? Privacy. This has become a big issue with, as we all know, with Cambridge Algorithmica, which has nothing to do with my university, by the way, despite what people say. For machine learning, we need to have lots of data. So we have to pool the data across users. There's no alternative. So there's some loss of privacy, if you don't do anything to protect yourself, is inevitable. But there are machine learning algorithms which preserve privacy. It's just that they're more difficult to use and they're more expensive and they're less efficient use of data. And to do it properly, you need to design privacy into your systems from the outset. So privacy comes at a cost. Do we think that we're going to be able to keep having our privacy assured without legislation? GDPR is a good step forwards, but in the world of personal assistance, I think we need more. And then trust. Do we trust the decisions that our personal assistants making for us? It's fairly obvious, it's a well-known fact, biased data leads to biased decisions. We train these models from data. But the problem is that the way we deploy these systems is that we deploy the system, we collect more data, and if the system's biased, then the data we collect is even more biased, and you get a reinforcement loop here. So any initial biases can be reinforced. And then, of course, who owns the personal assistant? If it's Apple or Amazon, do they have a stake in the decisions that your assistant makes? If you ask your assistant to buy some socks, it could buy it from Amazon or it could buy it from Waitrose. Does Amazon, do you really believe that Amazon's not going to tilt it in their direction? I'm not saying they are, of course. So bias is very hard to detect. We need some way of having trust in the decisions these systems are taking for us. And then liability. Well, again, I'm not sure. I'm not a lawyer. But it does seem to me that there's potential here for breaches of the law. Unintentional disclosure of confidential information. Breaches of the Sale of Goods Act. I could tell my assistant, hey, go sell my dining room table on eBay. Do I know that it's going to properly describe what I'm selling? Providing information which leads to an accident. Imagine driving down the motorway in your Tesla cars, which are now fully autonomous, and your personal assistants are talking to each other. Well, who knows what they might say to each other? Could cause an accident, who knows? And finally, exercising unacceptable forms of discrimination. So who is liable? You, the owner, or the person who supplied it to you? or someone else entirely. So to conclude, the current generation of conversational assistants are clearly here today. The public seem to love them. You know, people are buying Echoes like there's no tomorrow. Usage of Siri continues to increase week on week. So they're providing a useful service. And the technology is moving very quickly, and deep learning is going to accelerate that. I don't want to overhype this. We're not going to get into a situation of HAL or whatever the operating system was called in the film Her. We're a long way away from that, but we are close to having really quite capable, useful personal assistants. So if they become ubiquitous, it's going to create a number of societal challenges. And it seems to me that we need to think about these challenges now rather than after the event, which is what seems to have happened with Facebook. Thank you.
Oh, thank you, Steve. Next, we have a colleague of mine from Oxford, Suzanne Aigrain, she's a professor of astrophysics at the University of Oxford. She's interested both in exploring the full diversity of planets and planetary systems in the galaxy, and in understanding the frequency and characteristics of other worlds that might be hospitable to extraterrestrial life, which means when AI is taken over here, perhaps we can move there. So she's going to tell us how she's been using machine learning in her research. Thank you.
Hi. So I'm going to tell you a little bit about how machine learning is already making a difference in astronomy and our ability to observe and understand the universe and our place within it. And perhaps it's not so much that we'll move to another planet when AI has taken over this one, but perhaps the aliens who come will be themselves artificial intelligence. Who knows? Machine learning is already being used in just about every subfield of astronomy to extract information from datasets that would otherwise maybe not have been uncovered. But this is becoming increasingly important, in large part because our datasets are getting enormous, and they are truly enormous. Part of that is the fact that we've seen in the last decade or so an explosion of time domain astronomy. Time domain datasets come with specific properties and challenges that make them very well suited for machine learning. And that trend will only continue in the next few years. And finally, it's not always the size of the dataset that matters. Sometimes it's really important to use machines to learn the properties of the data so that we can have exquisitely sensitive measurements of particularly important physical quantities, or so that we can find tiny signals that we would otherwise miss. So just to give you some examples of upcoming very large data sets that will revolutionize astronomy, or that corner of astronomy, but only if we can understand and use those data intelligently. The Square Kilometre Array will be by far the largest radio telescope ever built. It's currently under construction in South Africa and Australia, and you can see it consists of hundreds of these large dishes and also hundreds of stations consisting of individual antennae. And together, these will collect enormous amounts of data. So we're talking about several hundreds of terabytes per second. The estimated raw data flow is 5 times the global internet traffic of the planet in 2015. There's no way we'll be able to store all that data, let alone analyze it in the comfort of our offices. And so we're going to rely heavily on automated algorithms to select what to keep and what to throw away. And we have to have huge amounts of trust that these algorithms are doing the right thing. We can train them to look for the kinds of events that we already know and to find more of them. But how will we deal with the problem of finding the unexpected? So, for example, we don't want the SKA to throw away all observations of a new astronomical phenomenon because we didn't think it would be there. But most of the unexpected things the SKA will find will be junk. There will be artifacts caused by radio frequency interference, problems with the instruments. So there'll be a trade-off to be made here. Another time domain experiment, which will come with huge amounts of data and rely heavily on machine learning is the Large Synoptic Survey Telescope. This is a visible light telescope which will scan the entire sky in multiple colors every night, every 4 days, sorry. And it will generate alerts. It will look for transient events, things like supernovae, asteroids crossing the field of view, but it will generate, we estimate, of order 1 million of these alerts per day. We, of course, will be able to follow up all of these. And so we will be relying, again, on some kind of artificial intelligence to tell us what to follow up, what to devote the follow-up resources to. Now, today we're not at that stage, and I think it would be more accurate to describe what we're doing as machine learning rather than artificial intelligence. But we're going to have to move into that domain in the next decade or so. One interesting thing about the Large Synoptic Survey Telescope is that they have recognized the importance of training the young scientists, people who are doing their PhDs today, but will be analyzing the data from LSST. And so they've set up quite an ambitious program that follows individual students over 2 years and brings them together for weeks at a time, several times a year, so that they will be ready to analyze the data when the time comes. And that's something that we might want to take inspiration from. Another area in which there's a lot of very interesting development at the moment is the use of the power of individual citizens to help us analyze the data. So when expert astronomers just don't have the time to visually inspect, say, large quantities of data, we rely on members of the public. But increasingly, we're teaming the citizens and the machines. We're using machines to either select what is shown to the public or to make sense of the classifications made by the public. And for example, this is one project which does this using data from pan-stars to look for supernovae. Now, in the rest of my talk, I'm going to tell you a little bit about my own field, which is the search for exoplanets, and how machine learning is already helping us to do this in ways that weren't possible before. I'm interested in exoplanets because they help us put our planet, our solar system, and also the civilization that arose on the planet in its cosmic context. But planets are really hard to find and even harder to study in detail. So most of my work revolves around the transit method. So we're looking for tiny little dips in a star's brightness that occur when a planet passes in front of it. And these dips will repeat once per orbit of the planet. But the example I'm showing you here has an approximately Jupiter-sized planet going in front of a star like the Sun. And that causes a dip that's about 1% long. This is what the Earth looks like in front of the Sun. So that tiny little dot here is what we're looking for. That will cause a dip that's about 1 part per 10,000. Furthermore, it will last for 12 hours and repeat only once a year. In contrast, stars also have complex features on their surface. These are star spots caused by magnetic fields. These erupt, evolve, rotate with the star. That causes a very complex pattern of variability which completely overwhelms the signals we're looking for. And furthermore, the instruments we're using to look for these transits are not perfect. So this is the Kepler satellite, a NASA satellite that's been the most successful transit search ever. It's found thousands of exoplanets and revolutionized our understanding of exoplanets. But the data that it produces is still noisy. It contains all sorts of systematic effects, particularly now that the satellite has aged a little bit and some of its components have failed, which overwhelm the transits that we're trying to find. So this is what a light curve collected by Kepler just in the past year might look like. You're seeing some smooth, quasi-periodic variability here, which is due to star spots. And then this sawtooth pattern is due to the jitter of the satellite, the fact that it's not controlling exactly where it's pointing very well, so the star's moving around on the detector. We need to model these in order to see if there's any transits of an exoplanet lurking under all that variation. But we can't predict them from first principle. We don't understand enough about them, and anyway, these effects are inherently random, inherently stochastic. So we need methods that enable us to do that, but that also enable us to be realistic about how well we're doing it. So we need to propagate uncertainty throughout the process. And one very powerful machine learning technique to do that, to learn the noise from the data, but in a robust way, is called Gaussian process regression. And in my team, we recently developed a pipeline to do this for that particular data set. So here you're seeing the same light curve, But it's now been separated into its constituent signals, the instrumental effects at the top, the star variability at the bottom, and then when you subtract those two and look in the residuals, you can see some small periodic dips. Are those caused by a transiting planet? Well, before you can be sure of that, you have to sift through the large number of detections of events like this you'll see in a whole Kepler data set and distinguish between the real transiting planets and other things that look like transits but are actually caused either by stars passing in front of each other or by instrumental problems. This is another area where machine learning is becoming increasingly popular. So until now, this distinction, the vetting of candidates has been done using semi-automatic pipelines, which basically rely on predetermined calculations supplemented by visual inspection by experts, or in certain cases by citizen scientists. But recently, there's been increased interest in using deep learning to answer that question of which of the transits are real and which are fake. And in fact, this interesting paper unearthed two transits that had previously been missed in Kepler data. It's not that the transits weren't detectable, it's just that when users have to sift through so much data manually, they just can't sift down into the noise as far as if you can do it very efficiently in an automated way. But I should warn that this is still very new, and one of the challenges for astronomers when using these techniques is that actually we're treating them as off the shelf, but if we don't understand how they work, we can't adapt them to our problems very well, and we can't understand what the impact of the choices we make in designing the architecture of a network like that is on the results. And that undermines confidence in the results. It also undermines their efficiency. So at the moment, this approach, although it found two planets that were missed, is still not as powerful overall as the more deterministic approaches that are the state of the art, if you like. Once you've found an exoplanet, you can also try and measure something about its atmosphere. There's many ways in which you can do this, but most recently, there's been an increasing interest in looking at what happens when the planet goes behind the star. It disappears, and so if you look at the difference between what you saw when the planet was next to the star and what it was behind, you can get a spectrum of the planet. All the light that was reflected or emitted by the planet disappears, and the difference tells you what the planet contained. We tried this a few years ago with one of my students with the Hubble Space Telescope looking at a hot Jupiter, a planet like Jupiter but orbiting very close to its star. And we thought we might be able to see light reflected by clouds in this planet, which we suspected should form there. And these clouds are actually made of molten rock. This is a very exotic kind of planet. The sort of signal we're looking for, though, is absolutely tiny. We're talking about maybe 1 part in 1,000, 1 part in 10,000. This is the raw data we got back from the telescope. In the top panel here, you're seeing the data as a function of time. Hubble gets eclipsed by the Earth every now and then, so the data has interruptions. We've divided up the data into violet and blue lights, and we're trying to see if the depth of the eclipse is different in these two channels. In the raw data, you just can't see anything. It's all dominated by systematic effects that are to do with the telescope. But we were able to model these in a way that we are confident is robust, and to extract measurements of the eclipse depth in these two different channels that tell us something about the content of the atmosphere of this planet. This is the sort of thing we'll need to do in the future much better if we are to search for actual signs of life on an exoplanet. This exoplanet is very unlikely to support life, but in the future we'll be doing this to a much greater degree, and we might do things like detect ozone in the atmosphere of an Earth-like planet using these techniques. So this is just an artist's impression of the color of this particular exoplanet as it would be seen by the human eye that we can directly derive from that particular data set. So I'm just going to wrap up with a few thoughts that I just leave on there. We need machine learning, but we shouldn't just be clients for machine learning. We need to get directly involved in order to make the most of it, and that means we need better training as well.
Well,
thank you, Suzanne. I think a lot of machine learning, it's all about commercial applications, so it's really nice to see how machine learning is being used in fundamental research, especially for a place like here, the Royal Society. Next, we're going to hear a story very much to do at the heart of machine learning at the moment in applications, which is to do with health. And I'd like to invite Antonio Cremonesi, who's working at Microsoft, and he's using machine learning to look at especially medical imagery, and he's going to be telling us how effective AI is in looking after patients. Thank you.
Just 2 seconds. Right, good evening, everyone. I'm Antonio Cremonesi. I work in Microsoft in Cambridge, near the station, in fact. And I'm going to talk to you about Project InnerEye, which is a research project that has been going on for a few years already in Cambridge, and it's to do with the application of machine learning to the analysis of radiological images. So I'm talking about CT, as in computed tomography, or MR, magnetic resonance images, of patients who have been diagnosed with some condition. So what can we do there? How can machine learning help the practitioners, i.e. the clinicians, radiologists, or surgeons, provide better care for the patients, and ultimately the patients would be able to benefit from such techniques. By the way, I don't know what AI is. I don't know what intelligence is, because those concepts are very, very difficult to define. But I do know a little bit, perhaps, about machine learning. And what I know and understand is that machine learning underpins AI. But in this talk, I prefer, just like Suzanne said earlier, to talk about machine learning, because it's much more concrete, it's easier to define, and we're talking about algorithms, which, given some input, can make some predictions. In this case, given images, we can predict where the tumor is, or the aneurysm, or multiple sclerosis lesions, as I will show in a minute. And so, just to make it doubly clear, there's been a lot of press around AI, some of it positive, some of it negative. There are some big machine learning luminaries, like Professor Jeff Hinton, who a couple of years ago, or 3 perhaps, said, deep learning is revolutionizing the world, including radiology. We need to stop training radiologists right now. And there we have Elliot Siegel, Professor Elliot Siegel from the University of Maryland, who is one of the biggest brains in radiology, who says, oh, maybe that's not correct. There is a lot of scope for radiologists, to do great work, together with, alongside AI. And so he thinks, like myself, that AI or machine learning will be more like tools to help radiologists. So what do we do in Project InnerEye? We have a very, very clear, I think, mandate to develop technology to assist medical experts. And we go even deeper and say we assist medical experts like clinicians, radiologists, surgeons, oncologists, in the areas of delineating or segmenting the disease and measuring it. So that's one of the trickiest things for human beings, experts, doctors to do, which is the measuring of tumors. It's relatively easy for expert practitioners to look at an MR image and say, this is tumor type X or Y. But it's very, very difficult, even in the most advanced countries or hospitals, to say how big the tumor is, and more importantly, whether it is growing or shrinking and by how much. So clearly that's very important to do. So I'm going to be a real geek now and try to hold your hands through a little bit of algorithmic details. Hopefully it's not going to be too complicated, but I care about this audience understanding a little bit in detail what machine learning is about, at least for this particular application. So we have images like the ones on the left. These are horizontal scans, horizontal slices through a 3D CT scan of 2 different patients, top row and bottom row. These are male patients of a certain age who have already been diagnosed with prostate cancer. Now you can see different structures. In particular, it's easy to make out bony structures like the femur heads and so on. And what we want to do is we want for our algorithms to automatically pick out and delineate different anatomical structures, different organs. It could be the bladder in yellow, seminal vesicles in purple, rectum, or in blue you have the femurs. All of this needs to be done very, very quickly and very accurately if we want for this technology to be useful really to the doctors. So what do? Typical of machine learning scenarios, we go and acquire a lot of data, and by a lot actually I mean quite a little because we only use hundreds of images. And this is really in stark contrast with what's going on right now in the world with deep learning. Much of the research community is enamored with deep learning, but it also comes at a cost where you need to acquire lots and lots and lots of images to be able to make those algorithms work. It's really important, especially when working in healthcare, when working with very sensitive patient data, to be able to train algorithms in a much more economical way with as little images as possible, and that's what we strive to do. So we have ground truth data, and we have expert delineations, and now we have to make a choice. What machine learning algorithm do I use? Fortunately, there is a lot that we can pick and choose. There is Gaussian processes, there is deep learning, in particular convolutional neural networks, but there are also good old decision trees. And decision trees have been around for quite a long time, and they turned out to be really effective at this problem, but also have a number of advantages over deep learning, particularly the fact that they are more economical to train and to run. They don't require expensive GPUs. But also, as it was mentioned earlier, it's important to be able to interpret what's going on. When the machine learning works, why exactly does it work? And when it fails, how can I make it better? How can I actually change the algorithm itself to make it work better? And it turns out that mathematically, I don't expect you all to understand exactly this slide, but just an indication to say that mathematically, algorithmically, there are theorems that show that decision tree type techniques can be mapped into neural network, therefore deep learning, more conventional, I should say, deep learning type of techniques. This doesn't mean that the two algorithms are identical. There are still differences, but it's important as machine learning researchers and practitioners to be able to choose and not just go with what everyone else is going for. So the way in which algorithms based on decision trees, in fact on ensembles of decision trees, which guess what, they're called decision forests, the way in which those algorithms work is by classifying each individual pixel, or in 3D we talk about voxels in those images, and being able to say what that voxel is. Does it belong to the prostate? Does it belong to the bladder or to the femur? And to do so, we make very heavy use of contextual information, so the space around that particular voxel. To be able to capture that efficiently, we know how to do it well using decision trees, and this is actually, turns out, a form of deep learning, but not using convolutional neural networks. So we end up with an algorithm which is a layer set of sets of decision trees, and they all learn from one another, and they're all cascaded, and the job becomes easier and easier for each of them. And in practice, what happens is that you end up with being able to segment different structures, such as the bladder here, the seminal vesicles, the rectum, in different patients. These are test patients, never used during the training and optimization phase, despite the fact that these patients have got different body shapes, different arrangement, slightly different arrangement of organs. Some of them might be bigger, some others might be smaller. By the way, these are all highly deformable organs whose shape and characteristics change within each of us during the course of the day, depending on whether we went to the toilet or we had too much to drink or we had too much to eat. So it's really important that we have that level of flexibility. I care also about giving you a live demo, which I know is a little risky, but let's try it out. So here I've got one of the applications that I've built, and here you can see some pre-canned results of the segmentation obtained in 3D for a patient CT scan. We can look at the bladder, we can look at the femur, we can look at the prostate, the back, and even highly deformable structures like the rectum. This is particularly important for radiotherapy, where you need to target very precisely where the tumor is and avoid the organs which are healthy. They're called organs at risk. We can apply this technology not just to CT images like the one you saw, but also magnetic resonance images, such as this one, where it's very clear that there is something really nasty going on there. This is one of the most deadly tumors that patients unfortunately might have. It's called a glioblastoma. So this one I'm going to run it completely live, and what I'm going to do, even if I have only 0 seconds left, is I'm going to click on the automatic segmentation. I'm going to choose the glioblastoma model through a list of services that are available for us on the Microsoft Cloud. These are services that we have developed. And now I click Start, and this is going to take only 15 seconds. So what happens live right now, my computer is connected to the Royal Society Wi-Fi, is that this image is being anonymized, all patient information removed. It is being compressed. It is being encrypted, sent over to the Azure cloud, where there is this API, this library waiting to analyze this image, walking through every single voxel, and by magic, while I was talking, the tumor has been segmented and returned to me. So now I can look at it in 3D if I want to, but more importantly, there is the nasty tumor, unfortunately. More importantly, I can actually measure how big it is. So I get the volumetric measurement. It says nearly 32 cc's in this case. Now, none of this can be done today, which means that, for instance, chemotherapy patients have to go through very nasty treatment with a lot of undescribable side effects for 3 months before you even know if the treatment is working or not. Wouldn't it be great if we were able to know after 2 weeks, perhaps, if the tumor is regressing or keeps growing? Because I'm out of time, I'm going to stop here, and I suppose we're going to take questions afterwards.
Our next story is about climate and weather. We had a lovely day today for you to queue outside, but I think on Monday, I'm not sure it was such a great day. But we're going to talk a bit more grandly about the climate of our planet. And we've got Professor Dame Julia Slingo, who is currently at the Cabot Institute for Environmental Research at the University of Bristol. She was formerly chief scientist at the Met Office, where she led a team of over 500 scientists working on a very wide portfolio of research that underpins weather forecasting, climate prediction, and climate change projections. So she's absolutely well placed to tell us how AI is currently helping us to understand our climate system.
Well, so like I think nearly all the speakers, we all struggled with AI and machine learning and what does it all mean. And I'm going to just take you in a slightly different perspective, because what we can see here is not the real world, it's a simulation. And I wanted to introduce the idea of simulation as being really an important part, potentially, of AI, or artificial intelligence, or as one of my colleagues has called it, augmented intelligence. And what can we learn about our weather and climate from simulation? And of course, it's through simulation that we make predictions. And I think, in many respects, my field of weather and climate is one of the very few where we can predict with some level of confidence, and we can debate this, what our weather might be like in the next few days and what might be happening to our climate as a result of what we're doing. And we can do that because we're bounded by some very fundamental laws of physics. And it's hard to think of any other areas where prediction in this, with such a robust scientific basis, takes place. And we can look at economic models and debate those too. So this is a simulation, a free-running simulation from a climate model. It's in 3 dimensions, evolving in time, and we can see the clouds, and it's a pseudo infrared image, so the white clouds are the high clouds and the grey clouds are the lower ones, and we can see the weather systems propagating around our planet. And if it was a bit darker, you'd see the sun going past and heating up the land and so forth. So that's a model of a simulation, and actually it's that sort of system that underpins every weather forecast. So I would argue that AI is in every weather forecast that we make. This is for Saturday, made yesterday. We're heading for a very nice weekend in the south, I have to say, which is good. And it's behind every climate prediction. And this is the classic curve we've got so used to seeing. I call taking the planet into uncharted territory, at least in terms of human civilization. So, actually, we've been doing machine learning and AI, I would argue, in weather and climate for a very long time, but not in the way that we understand it today. This is Gilbert Walker, who's a great hero of mine, and he worked a lot on the Indian monsoon and tried to understand why the Indian monsoon failed some years. And he said, I think that the relationships of world weather are so complex that our only chance of explaining them is to accumulate the facts empirically. That to me sounds like machine learning. He didn't have a machine. Well, he did have a machine. He had a human computer, and he got hundreds of his Indian staff to do lots and lots of statistical correlations of all the data that he could gather from around the world. And he discovered the Southern Oscillation, the North Atlantic Oscillation, and so forth. And now we know the Southern Oscillation is tied up with El Niño in the oceans. And we've had AI through Lewis Fry Richardson, who was very early in his life, his career, he started talking about weather prediction by numerical process. And he had this vision, and this is his weather machine, of being able to do weather forecasting by solving the differential equations, such as the fluid motions and so forth. He did actually make the first numerical weather forecast. It took him 6 days, and he did it in his spare time, and he got it wrong. But he said, perhaps someday in the dim future, it will be possible to advance the computation faster than the weather advances. But that is a dream. And of course, it is now a reality. So let's just look at what happens when we do that. And this is AI and numerical simulation today. We have these very complex codes that model the Earth's atmosphere and the Earth's ocean and land surface, based on very fundamental equations of physics, and we use sophisticated mathematics to integrate these equations forward in time. And to do that, we have to have very large supercomputers. This is the latest machine that we procured while I was chief scientist, and you can see that it does a lot of things and stores a lot of data. And it needs to do that because when we make a weather forecast, the first thing you have to do is to know what the state of the atmosphere is today. We need to observe today's weather, not just in the UK, but over the whole world. And so we gather a vast amount of data, observations, and process them. And we process over 100 million observations every day. And using actually some machine learning techniques called data assimilation, we are able to produce a three-dimensional description of the state of the atmosphere and indeed the oceans today, now. And from that, we can then use that to actually make a weather forecast. So here we go. We're running the computer simulations, just like the one I showed you at the beginning, a global simulation at a particular resolution, discretization of the problem, and then we refine that with a limited area simulation. And this is the example of rainfall on a front passing over the UK. That's what's going to give you your weather forecasts that you see on the BBC. But to do that, we've had to do a huge number of calculations, and we have to archive a huge amount of data. And we have to do that all in 2 hours, from gathering the observations to producing the forecasts. So this is a huge machine learning, but I would argue artificial intelligence exercise, because it's telling us about the future. It's giving us intelligence that we cannot possibly gain ourselves. And at the end of all of this, we produce a whole range of forecasts, not just what you see on the television, but for very many sectors, very many users, and they're all interpreted for the user need. This is hugely computationally demanding. Think about the terabytes of data that you have to interrogate that's constantly changing every day. And just think what AI and machine learning could do for you if you as a user could interact directly with all that data. Well, a few years back, I and the head of IT created something called the Informatics Lab. And we were one of the first people to get hold of Amazon Echo.
Alexa, what day is it?
Today is Thursday, April 7th.
Alexa, ask Dre what I should do today in Exeter.
How about a stroll?
What else?
How about a run?
Alexa, ask Dre when I should go for a run.
Where do you want to do that?
In Exeter.
Eighth at 2000 hours should be great for a run.
When else?
Eighth at 1700 hours should be great for a run.
Alexa, I'd go for a run to my to-do list.
I would go for a run on your to-do list.
Alexa, ask the Met Office for the shipping forecast.
So I'll stop that there. But the point here is that actually what's happening there is that he asks when he should go for a run, and through some very, very clever data analytics, they're going into those terabytes of data and finding Exeter. And later on, he would say, well, add the fact that I like going for a run to what you understand. Think about how we could use that sort of AI techniques to understand what our risks are to the environment today, tomorrow, next week, in the coming years, and customize it to your own personal needs. In fact, it's the virtual personal assistant example that we saw at the very beginning, but applied here to huge data volumes that we produce. But actually, there's more that you can get out of simulation. And we had some pretty serious floods while I was chief scientist. And the Cabinet Office came to me after the Storm Desmond in the Lake District and said, well, what's the plausible worst case for UK rainfall in the next 10 years? And I thought, my God, I don't know. I've observed the weather. We have observations for 100 years. But 100 years is just nothing when you know the myriad of weather systems that you can experience. So we drew on something that's to do with chaos theory. So this is AI and worlds that might have been. And we all know the saying by Ed Lorenz that one flap of a seagull's wings can forever change the course of the weather. And we use that to produce probabilistic predictions. But actually, it also says that the world that we observed for the last 100 years is only one of the possible ways in which the weather could have evolved in those 100 years. So can we find other plausible alternatives to what we've observed by using model simulation that's more extreme than anything we've experienced, at least in our memories and in the humans, in the society in which we live? And the answer was yes, we could. And we did this in just actually a few weeks because the government required a very quick answer. But here we are, we've got 35, we're looking at southeast England rainfall across the winter months. We've got 35 observed winters, but in my back pocket I had 1,400 simulated winters. So I had 40 more samples for the current climate. And the model was pretty good at simulating rainfall over southeast England. And what you can see here is that these are the observations, and actually that was January 2014, Thames flooding. It was an extreme well outside past experience. But when we look at the model's got one that's even more extreme, and actually there's a whole cluster of them here, which were certainly more extreme than we were expecting when we started in 2014. And you can see that we can actually find a whole lot of extremes at both ends of the distribution. And it allowed us to say that what the risk was of an unprecedented, at least in the observational record, an unprecedented extreme in any year or in any decade at different levels of risk. So this is really exciting because through simulation we're now building up synthetic event sets. And if you could actually have a really large synthetic event set, think how you could actually quantify your levels of risk and return period. And we can also use AI, if you like, simulation, to look at a world that would have been without our actions in the last 100 years since the Industrial Revolution. And this is just an example here of climate, of European summer temperatures. The observations are in black. Lots of natural variability, very difficult to detect a climate change signal. We've heard about detection methods. Same problem here. But look where it goes after about the year 2000 up here. The red swath are the simulations, the envelope of a lot of simulations that characterize the natural variability. And so they give you an envelope of what is reasonable for the current climate. And we can see that the observations lie within that envelope. But when we take out the greenhouse gas forcing, the CO2, without human influence, the world that would have been if we hadn't burnt fossil fuels, then that's the green swath. And we can see that in the last decade or two, for European summer temperatures, we are now well outside the world that would have been. That, for me, is artificial intelligence. It's about the use of simulation to tell us very important things. And of course, what it can also do, in this case, in my examples, what the world might be like in the future, depending on what we choose to do. And this is from a collaborative project called Avoiding Dangerous Climate Change. And these is looking now at all the impacts on us as individuals in interpreting all that weather and climate information that comes out of the simulations in terms of things that we will have to deal with, either personally or as businesses or as governments. And what we know, of course, now is that between 20 and 70% of these impacts can be avoided by staying within a 2°C target. We could not have done that without some huge data analytics, some huge simulations, and I would argue really a fine example of AI in action. So what about the future? Well, I think that the changing landscape of weather and climate risk is a major challenge for us as a global society in the 21st century. And we can see that just in this diagram here. I call this the circle of securities. These are all the things that we depend on for our health and well-being. And in the middle are all the things, the big challenges of the 21st century that will determine whether we are secure in all these aspects. And it's not just about weather and climate, it's weather and climate in the context, of course, of urbanization, megacities on coasts massively exposed to things like sea level rise. It's about population growth. It's about limited natural resources, of which water will become arguably the most precious. And it's how we are going to interact with that system and understand it, I think is going to be a huge challenge for machine learning, for systems like AI that allow us to personalize and allow us to make decisions on different aspects of our life and how we handle environmental risk. And it's worth noting there are 3 huge international agreements in 2015, We know about the Paris Agreement, but the Sendai Agreement to deal with disaster risk reduction, huge area of endeavour out to 2030. It's a fantastic example of how we can use machine learning to deal with multifaceted, very complex issues, and of course the Sustainable Development Goals. And it's worth recalling that actually we are exposed to extreme weather and climate events, and for many people, particularly in the developing world, these threaten to derail the sustainability of economic development and social welfare. And so we have to find the right ways to use our data, and it's big data, to extract the relevant information at speed and communicate it in a way that a user, a human being, can take on board and act. So I think AI machine learning is going to enter my field big time in the coming decade or two. So thank you very much.
So if I could invite our panelists up onto the stage, and we now have a chance to open up. We've extended the evening until 7:45, no longer than that because I have to get to see the Arsenal match, which starts at 8:05. I don't know whether any predictions using machine learning for whether we're going to get through against Atletico Madrid, but in some ways I think the public has seen so much about machine learning or AI in the movies, and it's always very dystopian. And I think the 4 stories we've had today really show just what an amazingly positive effect this technology will have and could have on society. We were going to have a dialogue between us, but I think I'm really keen to open this up to questions as soon as possible. So I'm going to ask you what you would like to ask our panelists. I think we've got some microphones that we can bring to people. There's already one here. I think what I'll do is take 3 questions, so we have a range of questions, and our panelists can try and address them all. So the first question I can see at the back there, and then we got our school group here. So we've got 2 questions from the school groups. That would be great. So if we can get the mic there after. So let's hear our first question, please.
Is this on?
It is.
Okay. Thank you. Thanks first for fascinating presentations. What will the dawn of quantum computing mean in each of your fields for the use of AI and machine learning and data analysis? Thanks.
Great, that's a great question. We'll get next question. I think the students, if you put your hand up, great, excellent.
Hi, my name's Alistair.
Hello, Alistair.
Hello. I just wondered, does AI go far enough to affect whether researchers are needed as much or as doctors are needed as much? Does it take enough of the pressure away because it does most of the work now? Or are we way too far off of that?
Good, that's a great question, the future of work. And the third question at the back, if we could get the microphone to the woman at the back, right in the corner.
Hello, my name is Sahana Navneethan, and my question is that looking at medically, I see that it could be a very successful use for AI. But the question is, do you think that, considering that most countries right now are actually, in fact, in recession, do you think that this could be provided to all people free of charge, and do you think that all patients will open up to letting their information be used in this way?
Yeah, so a great range of questions. So from quantum physics to economics, and also the future of work, which obviously you touched on with radiology. So why don't we start with the future of work? Sure. Yeah, I mean, are you out of a job? Are our scientists out of a job?
Yeah, that's a great question about the future of jobs. And my opinion is, like all technology will have, in the past, have affected jobs. AI and machine learning is also likely to affect jobs, right? So I think, we can be sure of that. In which way, there is a lot of uncertainty, but the other thing I'm sure about is that people like radiologists will still have a job. It might look different. In fact, one of my radiologist friends says, It's not a matter of whether AI will replace radiologists or not. It's for sure that radiologists who use AI or understand AI will replace radiologists who don't. So it's a very different proposition. So it's about educating ourselves, it's about learning this new world and these new tools. And the question was also about the economic side of things. So the fact that we have a new technology that can help hospitals doesn't necessarily mean that costs are going to increase. Unfortunately, there is so much inefficiencies in the NHS that companies can be paid for the technology. At the same time, the overall cost gets reduced. So what we're working towards is saving the NHS money, as well as improving patient outcomes, and potentially, of course, there are many ifs and conditionals, and reducing times that clinicians have to take to perform their daily job.
What about that economic question when it comes to...
I was going to comment on the quantum.
Oh, go on the quantum, yes, that's great, yes.
The question about the quantum computing raised a couple of things in my mind. One of the things is, at the moment, when we talk about trust, if we have a big AI system taking decisions, how can we trust the results? One of the problems is that most of the algorithms that are used, there's no proof of convergence. And what you're actually doing is you're not obtaining an optimal solution, you're obtaining a good enough solution. And you never quite know how better or different the real good solution might have been. So clearly, this is very largely compute bound. Now, if quantum computing can really deliver multiple orders of magnitude improvement in compute, then we might be able to just get much better solutions. I think the other thing, which is completely orthogonal to that, is one of the things that does bother me is how much heat is being generated by these compute farms that are actually churning through all of this stuff. And Bitcoin, I think, is an interesting example. Bitcoin is predicated on searching with machine learning algorithms essentially for solutions to a fairly hard cryptography problem. And it's like mining gold. The value of the Bitcoin is determined by how difficult it is to find new Bitcoins. But the cost in energy that's now being expended searching for Bitcoins, completely pointlessly in my view, is I think, a serious consideration. And maybe quantum computing or other forms of computing can be much more efficient and therefore stop this, making the climate problem much worse.
And in your fields, how do these three questions impact?
Well, certainly in terms of whether scientists will be put out of a job by machine learning, I think it's more a question of we're generating data so fast that I think machine learning will save us from some kind of singularity event. I think with machine learning, the things we'll be able to do with that data will change. And there's certainly also a case, as Antonio mentioned, of scientists who know how to use machine learning will certainly replace those who don't over time. One question, I'm not a specialist, but one question that I find interesting about the use of machine learning in areas of importance to the public, and particularly in things like medical care, is the ownership of the process and the fact that when we're relying on technologies which often are not open source to make things like medical diagnosis possible, are we essentially making our medical system a hostage to the commercial interests of these companies? That I think is an area that is worth debating.
Of course, one of the best ways to get trust in something is to make the source open source, and then you can read it. If you don't believe the algorithm, at least you know what's being used.
Make it open source and make it so that others can build upon it.
Because citizen science have been involved in climate data and collecting rainfall for centuries, which the Met Office used. Is the role of scientists in climate science going to be threatened at all? Or?
I don't think so. No, the whole issue of prediction requiring actually the sort of nature of the simulations that I showed, and actually we are still massively constrained by compute power in terms of the granularity of those simulations and what they tell us about what's happening locally and increasingly within our cities. So I don't think that, you know, and we're never going to observe every little bit of our environment in all the detail. So it's how do we make the optimal use of all the observations, and including what the citizen makes, and we have a wonderful program on that at the moment, actually. But how do we make the optimal use of those observations within a simulation system that then can fill in all the gaps and take all that information forward in time? Quantum computing is potentially a major breakthrough. We're going to have to rewrite our 2 million lines of code, though, to use it. And in the process, actually, we're really beginning to look at how can we use machine learning from very fine-scale simulations to inform how to represent complex processes in the atmosphere, like turbulence, like cloud formation, within our coarser-grained models. So actually, we're really getting into using neural networks and all those sorts of concepts to actually try and introduce machine learning into how you really can write new sorts of codes. And of course, machine learning can also fill up the number of simulations. We can produce emulators of the climate model, which run much more rapidly than the full climate model, but allow you to fill up the probability distribution of what might be likely outcomes, say in 10, 20, 50 years' time, depending on what things we decide to do to reduce our carbon emissions and other aspects of how we interact with the environment. Potentially absolutely wonderful future.
Well, okay, that is very relevant to a couple of questions that we've had come from downstairs. Our viewers downstairs have sent some questions up. The first one is from Kieran, who says, do any of the panel see any threats emerging from superintelligent AI? So we've had a very rosy story, but what about the threats? Are there things that you're worried about where your work might go? The other question is, what new institutional arrangements will be needed to assess ethics of AI, and how can those be funded? Steve, you certainly raised those issues, but didn't answer them.
No, I didn't. Well, I think organisations such as the Royal Society, are making a good start on this. I think legislation is terribly difficult, but if we could have at least a sort of voluntary consensus code of ethics that we could aim towards, I think that would be very helpful. Answering some of the simple questions I asked, on the screen there.
So I want to take this question from two different angles. One of them is, as a scientist, the way in which we use machine learning or AI still has to be governed by the principles of scientific inquiry. And that means that we can't just be making a decision without justifying it. We need to understand why we're making the decisions we are in the process of designing our tools. And we also need to always have an estimate of the confidence of our predictions. This is one of the ways in which AI is extremely powerful in generating simulations of processes that we can't observe multiple times. But it also means that we need to design the AIs, and that means we need to engage with the design of the algorithms, either by working with experts or by understanding them better ourselves. So I think there's a lot of culture change needed in the scientific community to engage with the mathematical underpinnings of machine learning well enough that we understand what we're doing, essentially. And then more generally, in terms of the way AI impacts society, there's all these questions about how individual users' personal data is shared, or how people might be delegating decisions to personalized assistants. And I think one of the guiding principles that we could move towards is the notion that the user needs to be able to exert control over the way in which the AI interacts with them. As far as the medical applications of AI, for example, we AI is one technology among many, and we can learn from the development of previous technology, whether it's drug development or anything like that. We've had to regulate that as well. So there's a lot we can learn from our previous experience with emerging technology in how to regulate artificial intelligence.
I had another couple of quick thoughts on the ethics, which is clearly very, very tricky, right? Yeah. So to me, it's obvious that we need to engage with the public, and again, this event helps with that. In my area in particular, we're engaging with patients, right? So it's not true, or it's not completely true, that people don't want to share their data. My data is private. I don't want, other institutions or organizations to access my data, because when you talk to actual patients and you explain what the benefits of sharing the data might be, then most often than not, they're very, very happy to share the data in an anonymized and respectful and sensitive way, in the hope that research can help other people, if not directly themselves. But also, you probably know Professor Luciano Floridi from Oxford, who is working, doing some incredible work on the ethics of data sharing, in particular for healthcare. And there are a lot of really interesting, if not thorny issues. But at the same time, he asks the kind of questions which are really fundamental. Like, imagine that I'm a hospital and I've got a lot of patients' data, which through this type of technology I know could help diagnose disease better or find a cure for nasty diseases. Is it ethical for such hospital to keep that data locked away and inaccessible? So that's the same ethics question, but the other way around. I think it's very profound to ask ourselves these sort of questions.
Julia, any final comments?
Well, I think, one of the issues with AI is going to be knowing how the machine has arrived at the answer. And I know how difficult it is for us in my field to try and understand why sometimes the forecast is badly wrong, bearing in mind that we always do a probabilistic forecast. So we've even assessed uncertainty in very formal ways. So I think this is going to be a real challenge, because if you give wrong advice, there are legal and social implications. And in my field, at least, we know that the system is bounded by some very fundamental physical laws. It does constrain the solution, and we have very sophisticated techniques that we've developed over many years to evaluate the simulation and assess its shortcomings or not. And I think, we need to do the same thing with AI.
I think this is going to be one of the big challenges
absolutely.
about explaining where that intuition, sometimes we can't explain our own intuitions, but we feel that it should be able to articulate, and I think that's perhaps one of the new challenges.
And it comes in, with how good are the learning data that are used, exactly. And what's the provenance of those data, and are they robust, and also tracking data is also metadata, as we call it. It's going to be absolutely crucial in all of this.
Well, it's clear that we really could have put this meeting into quantum superposition and had many different questions going on, but there was only one world we could live in, and unfortunately, kickoff is approaching. Can you please join me in thanking our panel for a great range of stories?